Now that we have discussed the three different methods on how to solve a system of equations, we are now going to talk about special systems. So each of the methods that we discussed so far have advantages and disadvantages. So the main idea is to try to pick the best method to solve the system. The more that you are familiar with each method of solving a system, the easier it's going to be to decide which method would be best to use. So, if we look at example 1 in 7.5, since the second equation is easily solved for x, we're going to do that first and then use substitution. So we had x minus 3 equals negative 2 as the second equation in example 1. So we can see here how easy it would be to just solve for x. And now we can use substitution since we know x equals 1. So we'll take our first equation, x plus y equals negative 3. We'll use substitution, and now we can solve for y. Now we know the solution to the system is 1, negative 4. For example 2, there's not a variable that's easily solved for. So what we're going to use the elimination method. So we have 3, 4, 2, and 7 as our coefficients. So in order to use the elimination method, we have to pick a variable, and we have to make the coefficients of that variable the same or opposite. If we make them the same, then we can subtract the equations, and if we make them opposite, we can add the equations. So we're going to try to eliminate x, which means we'll have to multiply the first equation by 2, and we'll have to multiply the second equation by 3, which would make the variables the same, or the coefficients the same. So we'll actually multiply by negative 3, so that way they'll be opposite. So we have 6x plus 8y equals 6 after multiplying our first equation by 2. And our second equation becomes negative 6x plus 21y equals negative 3. So now our variables are, the coefficients on the x are opposite. We have 6 and then negative 6. So which means if we add it together, the x terms would cancel. They mean as 29y equals negative 87, which means y is negative 3. And since we know y is negative 3, we can substitute it back into, let's put it back in the first equation. We'll put that back in the first equation, and we can now solve for x. It becomes a two-step equation. Add 12 to both sides, then divide both sides by 3. So now we know that our solution is 5, negative 3. In example 3, both equations are already solved for y. So since they're already in slope-intercept form, the easiest method to solve that system of equation would be to graph them. We're going to graph y equals 3x plus 5 and y equals x minus 3. So when we graph them, you see that their solution is the point negative 4, negative 7. Alright, so systems of equations can also be classified. The way that we classify them is according to the number of their solutions. So, inconsistent systems have no solutions. So no ordered pair makes both equations true. So that means there's no answer. If you have a consistent system, that means you have one or more ordered pair solutions. So far, most of the systems that we have done have had one ordered pair solution, which means most of our systems have been consistent. Now, if we just have one solution, it is called an independent system. Again, most of the problems that you have been doing up until this point have had just one solution, one ordered pair as the final answer, which means that most of the problems that you have been working on, most of the systems that you have seen, have been consistent, independent systems. Now, every now and then, you'll have infinitely many solutions. And this is called a dependent system, when you have infinite solutions. We can also look at the graphs of our systems. So inconsistent systems, where there is no solution, the graphs of inconsistent systems are parallel lines because they never cross, they never intersect. There's no point of intersection, because if there was a point of intersection, then that would be a solution, which means it would be consistent. So inconsistent systems are parallel lines. Consistent independent systems have intersecting lines. And consistent dependent systems have coinciding lines. Coinciding lines means that the lines are the same. They're on top of each other. So looking at example 4, we have x plus y equals 7 and x plus y equals 5. So for this example, we have no solution, okay, because we ended up with the statement 0 equals 2. All of our variables canceled, and we got 0 equals 2. So we know that there is no solution, so we know that the type of system is inconsistent. But what I also want you to look at is the statement 0 equals 2. When you get a false statement, that's how you know that your system is inconsistent. When you get a false statement after all the variables have been eliminated. So if you're trying to solve a system and your variables disappear, they cancel or they're eliminated, and you end up with a false statement, then you know that your system is inconsistent. If you were to graph those two lines, the x plus y equals 7 and x plus y equals 5, you would see that they're actually parallel lines. Again, if you can see that they're parallel lines, then you know that they're going to be inconsistent and there will be no solution. So both lines have the same slope, but different y-intercepts. All right, let's look at example 5, where it's x equals negative y plus 2 and 3x plus 3y equals 6. So in this system, when you try to solve the system, the variables disappear again. So you might think, oh, okay, the variables disappear. That means that there's inconsistent, no solution. But that's not true, because when your variables disappeared, you got a true statement. So in this case, we got the statement 6 equals 6. Remember back in example 4, we got 0 equals 2, and that was crazy. 0 doesn't equal 2, and that's why we knew that was inconsistent. But in example 5, we got 6 equals 6, which is a true statement, which means that there is a solution. It's just that there are an infinite number of solutions. If we graph those two equations, you can see that the lines are coinciding, which means that they're right on top of each other. They make the same line. And then both lines are going to have the same slope and the same y-intercept because they are the same line, and they'll look identical if you put them in slope-intercept form. All right, let's review. Consistent independent is going to have one solution. The graph is going to be intersecting lines, and the slopes are unequal, which means they're not the same. So if you have a consistent independent system, you're going to have one solution. They're going to be intersecting lines if you graph them, and the slopes are not going to be the same. So you'll have a single ordered pair results from either substitution or elimination. Next type, consistent dependent. And this category, all the points on the line are correct. So you have the infinite number of solutions. Your graph, if you were to graph the two equations, would look like coinciding lines, which means that the slopes and the y-intercepts are both equal. And then a true statement results from substitution or elimination, which means your variables will disappear but leave you a true statement. Now you have inconsistent. Inconsistent, there's no solution. The graph looks like parallel lines, and the slopes are equal, but the y-intercepts are not equal. And then a false statement results whenever you try to use substitution or eliminations. Your variables will disappear or be eliminated, and it will leave you with a false statement and an untrue equation. All right, in example 6, we want to know which equations form a consistent dependent system and which ones form an inconsistent system. So, equation 1, we have 3y equals negative 3x plus 9. Equation 2, we have x plus y equals 4. Equation 3, we have negative 6x equals 6y minus 24. You can actually take a look at page 304 to look at all three of those equations and write them down. If we're looking at equation 1, which is 3y equals negative 3x plus 9, if we put that into slope-intercept form, we would see that our slope is negative 1. We would also see that our y-intercept is 3. In equation 2, which was x plus y equals 4, if we put that into slope-intercept form, our slope would be negative 1, our y-intercept would be 4. Equation 3, which was negative 6x equals 6y minus 24, if we were to put that into slope-intercept form, our slope would be negative 1, and our y-intercept would be 4. So we're trying to see which ones are a consistent dependent and which one is inconsistent. So equations 2 and 3 describe the same line. The slope is the same and the y-intercept is the same. So they're actually in slope-intercept form, they look like the same equation. So those are a consistent dependent system because they're going to have infinite solutions, and that if we were to graph them, then we would see that they are the same line. They would be right on top of each other. Now, equations 1 and 2 are parallel lines, so they are going to be an inconsistent system because there's no intersection. If you needed help, if doing this example and you don't know how to find the slope and the y-intercept from an equation that is not in slope-intercept form, I need you to go ahead and look at the example on page 304, and they will show you how to find the slope and the y-intercept. All right, that is all for this lesson.